In Chapter 8, we will cover sampling methods and the Central Limit Theorem. The learning outcomes or objectives. First, we want to explain why populations are sampled and describe the 4 methods to sample a population. Then we will define sampling errors, and we'll see how to calculate sampling errors for the sampling distribution. Demonstrate the construction of a sampling distribution of the sample mean. If you have a population, then consider all possible samples of a fixed size that will give us a sampling distribution. So we will see how to construct the sampling distribution of the sample mean. Number 4, we will recite the Central Limit Theorem and define the mean and standard error of the sampling distribution of the sample mean. Number 5, apply the Central Limit Theorem to calculate probabilities. Of course, we discussed before why we sample, and there's many reasons why we take a sample. Normally, the population is large, and it's not easy to collect data from all of the population, or it might be very expensive to do so. But we take samples and we collect our data from the sample, and the results of the sample may adequately estimate the value of the population parameter, and that would save us time and money. We already discussed the reason why you might want to do this. It may be too time-consuming to contact all the members of the population. It might be impossible to check or locate all the members of the population. The cost, of course, of studying a large population, the cost of studying all items in the population may be just too much. Also, when we're sampling objects in manufacturing, testing will destroy the sampled items, and it cannot be returned to the population. But there is many reasons why we decide to take a sample to estimate a parameter for the population. This is what we do. We take a sample, we collect our data from the sample, and then we can estimate the parameters from the data that we obtain from the sample. There is 4 types that we will consider, 4 different methods of sampling. The first type is called simple random sample. Here, all members of the population have the same chance of being selected for the sample, and we will see examples of each type. The second type is systematic sample. A random starting point is selected, and then every kth item thereafter is selected for the sample. The third type is called stratified sample. The population is divided into several groups called strata, and then a random sample is selected from each stratum. The fourth type is called clustered sampling, where the population is divided into primary units. Then samples are drawn from the primary units. We will see examples of each of these 4 different types of sampling. Let's start with simple random sampling. This is the most widely used method of sampling. Here's a definition. A simple random sample. A sample is selected so that each item in the population, or each person in the population, has the same chance of being selected. Here is an example. We have 750 Major League Baseball players. A committee of 10 players need to be formed, and you need to select 10 people from the 750 players to form the committee. But to make sure every player has equal chance of being selected, you can write each name on a piece of paper, place the names in a box and mix them, and then draw 10 names. This is an example of a simple random sampling. طبعا يعني also another way to select simple random sample is using tables. There are tables for random numbers. This same examples of players, 750 players. We can طبعا select the committee again to make sure every player has equal chance. Use the tables of random numbers that we see in the slide. So you can prepare a list of all the players. There's 750. طبعا you can number them 1 through 750. You can randomly pick a starting place. طبعا the players now are numbered from 1 to 750. So you can from the tables you can randomly pick a starting place. This is from the random table. Select 10 3-digit numbers between 1 and 750. طبعا each of these digits will correspond to one of the players. These digits are selected randomly. For the selection of the 10 players will be a random selection. The second type of sampling method is called systematic random sampling. If you do not have a list of the entire population to begin with, you can use this method, systematic random sample. And the definition for systematic random sample, a random starting point is selected, and then every kth member of the population is selected. And here is an example. This is a grocery store. Stud grocery store wants to study the length of time customers spend in their store. يعني how long do customers stay in the store. فطبعا they don't know all the customers. So when using the systematic method for sampling, you may randomly select the days of the week and the time that you will want to start sampling. This is now the starting point of the study. Then systematically select the customers that measure the time they spend each customer, how long they spend in the store. You're selecting a day of the week randomly, and also the time. You may decide I will start sampling on Wednesday, and the time also could be selected at random. And then you start selecting customers beginning at that time, and you can of course measure how long the customers stay and how long each customer stays in the store. Stratified random sampling. Here the population can be divided into groups based on some characteristic. Use stratified random sampling. We will see the definition, and then we'll look at an example of stratified random sampling. With stratified random sampling, a population is divided into subgroups called strata, and a sample is randomly selected from each stratum. Here is an example. The table here contains information about, or this is a study of 50 of the 352 largest U.S. firms. For 50 out of the largest 352 firms. Begin by identifying the strata, then use random sampling within each group based on the relative frequency to collect the sample. طبعا how many you select from each group depend on the relative frequency. For example, one way to do this, since these are companies, you can يعني divide them according to the return on equity. طبعا these are known numbers for each company. For example, the first group or the first stratum are those companies that make 30% return on equity. The companies that make 30% or over, turns out there are 8 firms. The relative frequency طبعا 8 divided by 352 is 0.02. The second stratum is those companies who make between 20 and 30. The third group are those companies that make between 10 and 20. The fourth group is companies that make between 0 and 10. And the fifth group are companies that have deficit, meaning that they have no return on the equity. فطبعا the number of firms is listed in the column, and the relative frequency is calculated. The sum of the relative frequency will be 1. And now how many you select from that group depends on the relative frequency. You know your sample size is 50, but you select from each group, you select your selection is based on the relative frequency for that group. The total number in the sample will be 50 companies. The fourth type is called cluster sampling, and that we do sometimes based on geography. Cluster sampling is a common type of sampling used to reduce the cost of sampling over a large geographic area. In cluster sampling, then a population is divided into clusters using naturally occurring geographic or other boundaries. The cluster are randomly selected, and a sample is collected by randomly selecting from each cluster. There may be too many clusters, but we select a certain number of those clusters in a random process, and then from each cluster we select a sample, and the sample is collected randomly. Here is an example. Suppose we wish to sample residents of the 12 counties in the greater Chicago area. Here طبعا each county, you have 12 counties in the Chicago area. You want to sample, take a sample from that area. You want to maybe question them about government policy or their opinion about government policy. So randomly select 3 counties out of the 12 counties, and then from each county you can select a random sample of the residents in each of the 3 counties. This is an example now of a cluster sample. Next, we would like to define sampling error. It is unlikely the mean of the sample will be exactly equal to the mean of the population. Now, just to remind you, when we take a sample, for example, we want to estimate the mean for the population. So we take a sample and collect the data, and then calculate the mean for the sample and use it to estimate the mean for the population. Now, it's not likely that the mean for the sample will be exactly equal to the population. After all, it is just an estimate. This sample mean is just an estimate for the population mean, but there is an error. There's always some kind of error. The sampling error is defined to be the difference between a sample statistic and its corresponding population parameter. We may not know, but if we know for example, the mean for the population, and if we take a sample and calculate the mean for the sample, then the difference between the two numbers is called the sampling error. Here is another example. The Foxtrot Inn, this is a hotel, small inn. The number of rooms rented in June The mean number of rooms rented, which is mu, is 3.13. This is now for all the rooms in the month of June. Taking 3 random samples of size 5, we find the sample means, يعني طبعا 3 different samples with 3 different means. The different يعني for each sample we calculate the mean. We find 3.80, 3.40 and 1.80 يعني for the different samples. If you want to يعني measure the error in each case, just subtract it from the mean for the population, which in this case we know to be 3.13. طبعا the error could be positive or negative, but it's just the difference between in this case it is the mean, which is the difference between the mean for the sample and the mean for the population. Next, we would like to consider the sampling distribution of the sample mean. Of course, the objective here is we want to determine how accurate the sample mean is. Yani, you take a sample from the population, calculate the mean for the sample, you are using it to estimate the mean for the population. But the question is, how accurate is this estimate? We'll start by defining the sampling distribution of the sample mean, and then we will see how to measure how accurate our estimate is. The sampling distribution of the sample mean, a probability distribution of all possible sample means of a given sample size. You can imagine طبعا a population and you're interested in a certain sample size. Now if you take different samples of the same size, you will get different means. طبعا the mean itself is a variable. The probability distribution of all the possible samples of the same size is called the sampling distribution of the sample mean. For a given sample size, the mean of all possible sample means selected from the population, it turns out that the mean for that distribution will equal to the population mean. Yani, looking at the distribution for the sample mean, if we calculate the mean for that distribution, it will be the same as the population mean. There is less variation in the distribution for the sample mean than the population distribution. Yani the value for the variance for the sample distribution of the mean will be less than the variance of the population. The sampling distribution of the sample mean tends to become bell-shaped. طبعا that would suggest in the sampling distribution under certain conditions will be a normal distribution. Here is an example, yani just to get an idea how to construct the sampling distribution for the mean. This is Tartus Industries, has 7 production employees, and this is your population. The hourly earnings of each employee is given in the table. First of all, we want to calculate the population mean, and then we'll look at the sampling distribution. In this case, we want to look at the sampling distribution of the sample mean for sample size 2. Yani consider every possible sample that have size 2 and calculate yani the mean for that distribution. We'll find out that it is equal to the mean for the population. What is the mean for the sampling distribution? طبعا, first we start by calculating the population mean, and then we will see how to calculate the mean for the sampling distribution, and it will turn out to be the same number. Fourth thing we would like to do is what observations can be made about the population mean and the sampling distribution. But here is the table that have a list of the hourly earnings for the 7 employees. طبعا the population mean is easy. Just add all those numbers in the table and divide by the number of data values. The population mean, or mu, will be $15.43. This is just adding all the hourly earnings for the 7 employees and dividing by 7. The next thing now, we would like to form the sampling distribution for the sample mean. Here the size is 2. We will list all the possible samples of size 2 and calculate the mean for that sample. فطبعا there is 7 choose 2 different samples of that size. So we're going to list them all, and طبعا each sample will have 2 people in it, and calculate the mean for that sample, and that will give us now the distribution for the sample mean. So here is the list for all the possible samples, and also we will look at the mean, add the 2 numbers and divide by 2. So every possible mean for every possible sample of size 2 is listed in that table. So these are now the different values for the random variable, which is the mean. So what we can do now is form the distribution for sample mean. So we would like to list all possible values for the sample mean and see the probability for that value. For example, for sample mean equal to 14, turns out that there are 3 samples that have that mean. طبعا we calculate the relative frequency. The relative frequency in this case will be 0.1429, and that is the probability for that value, the probability that the sample mean will be 14. The same thing we do for 15. Turns out there are 9 samples that have sample mean equal to 15. The probability is just the relative frequency, which in this case it is 0.4285. For sample mean equal to 16, there are 6 samples, and the relative frequency is 0.2857. Finally, for sample mean equal to 17, there are 3 samples that have that mean for a frequency equal to 0.1429. طبعا the sum of the probabilities, as you would expect, is equal to 1. And the number of sample means, there is 21 sample means. Now we're ready to calculate the mean for the sampling distribution. معناتها take all the sum of all sample means, divide by the total number of samples. Turns out the total will be 324. We have 21 different samples. If you divide 324 by 21, you get 15.43. Then the mean for the sampling distribution of the mean is equal to the mean for the population. This was طبعا number 4. What observation can be made about comparing the population and the sampling distribution, and the mean is the same. The mean of the distribution of the sample mean is equal to the mean of the population. This is something that was expected. It is true in all cases. The mean for the distribution will be equal to the mean of the population. Now, what about the spread? Here it will be measured by the variance. It turns out that the spread and the distribution for the sample mean will be less than the spread and the population value. In fact, we will see how to measure it exactly. We will be able, if we know the variance for the population, it should be easy to calculate the variance for the sample mean. The shapes of the population and sample distributions are different, as you expect, of course, since they have different variance, the shape will be different. In this graph here, we have a graph for the population distribution, and that represents the hourly earnings. And then the graph to the right is a distribution for the sample mean. And it is clear that they are different. Here is now the central limit theorem, which is an important theorem in statistics. The central limit theorem tells us if samples of a particular size are selected from any population, the sampling distribution of the sample mean is approximately a normal distribution. The approximation improves with a larger sample. And if you take the distribution for the mean will be close to or approximately normal. The larger your sample is, the closer it will be to being a normal distribution. طبعا if you take your sample large enough, then the distribution for the mean will be close to a normal distribution. طبعا there are conditions that will guarantee you that the distribution for the mean will be normal. For example, if you start with a population that follows a normal probability distribution, then for any sample size, the sampling distribution of the sample mean will also be normal. But the size, if you started with a population that's already follows a normal distribution, then the size of the sample does not matter. The resulting distribution will always be normal. طبعا you may not know the original population if it follows a distribution, but there are other conditions that will guarantees that we will have a normal distribution for the sampling distribution. If the population distribution is symmetrical, you will see the normal shape of the distribution of the sample mean emerge with samples as small as 10. طبعا احنا we already stated in the larger the sample is, the closer you will get to a normal distribution. With a symmetrical distribution, such as a normal distribution, and if you started with a symmetrical distribution, then samples even as small as 10 will be close to being a normal distribution. If the distribution is skewed or has thick tails, you may need a sample of 30 or more to observe the normality feature. In certain conditions, a small sample will not work. Here is the case, for example, if this distribution is skewed, the distribution for the original population is skewed or has thick tails, you may need a sample as large as 30 or more. You need a much larger sample so that you would get normal distribution for the sample. The central limit theorem is useful. It will help you. طبعا it's always nice to work with the normal distribution. One way to use the central limit theorem is to take a sample large enough so that your sampling distribution will be normal. Here are different shapes that will show you the sampling distribution, and you will see in the size of the sample is important. Here you have several types of populations, and you see different sizes of samples and the shape that the sampling distribution will take. For example, here for the first graph here appears to be a symmetric distribution. For even smaller sample will give you a normal distribution. The distribution for the sample will be normal. For there is several sample sizes, 2, you look at even 6, with n equals 6, the sampling distribution is very close to normal. And طبعا the larger the sample is, the closer you are to a normal distribution for the sampling distribution. So as you can see, there are several types. طبعا some of them require a larger sample, but in all the cases, if the sample is large enough, for example 30 or more, your sampling distribution will be normal, and that's exactly what the central limit theorem tells us. Next, we made a statement the variance in the sampling distribution is less. Now we already know the mean for the sampling distribution will equal to the mean of the population. What about the variance? We said the variance for the sampling distribution will be less than the original population. So now we will have a formula to actually calculate the variance for the sampling distribution. To start with, we already stated the mean of the distribution for the sample means will be exactly equal to the population mean. If we select all possible samples of the same size from the population, that will give you the population, that will give you the distribution for the sample mean. We will see that the mean for the population equals to the mean of the sampling distribution. What about the standard of deviation? The standard of deviation of the sampling distribution of the sample mean is called the standard error. The standard error of the mean, and it can be calculated using this formula. Sigma for x bar, now x bar is your sampling distribution of the mean. But that distribution, we already stated, will have a mean equal to the mean of the population, and here is how to calculate the variance for the sampling distribution, which we call the standard error. The standard error is equal to sigma, the standard of deviation for the population, divided by the square root of n. طبعا you can tell here, the larger your sample is, the less variation will be in the sampling distribution. There will be less dispersion in the sampling distribution of the sample mean. The value can be calculated. It is equal to sigma over the square root of n, and we call this the standard error for the mean. طبعا we will look at examples how to calculate the standard error. If the population follows a normal distribution, your population already follows a normal distribution, then the sampling distribution of the sample mean will also follow a normal distribution. And that's true for any sample size. That is, if you start with a population that already follows a normal distribution. If the population is not normally distributed, the central limit theorem tells us you need a larger sample. You need a sample of at least 30. If you start with a population that's not normal, then the size of the sample should be 30 or more, so that the sampling distribution will be normal. Assume the population standard of deviation is known, then you can calculate the standard error using the formula. To determine the probability that a sample mean falls in a particular region, use the following formula. Z is equal to x bar minus mu divided by sigma divided by the square root of n. Now remember, we stated if the population, the original population, is normally distributed, or if your sample is large enough, like 30 or more, then the result is a sampling distribution that's normal. So you can use the z tables to calculate probabilities. So then, to determine the probability that a sample mean will fall in a particular region, use this is calculating the z value. If the z value, take x bar, which is your random variable, which is the sampling distribution, minus mu, which is the mean, divided by the standard error, which is the standard of deviation for the sampling distribution, which is equal to sigma divided by the square root of n. But this is actually the same formula we used before to calculate the z-value, but this is done now especially for the sampling distribution. Since we know the mean is equal to mu and the standard of deviation is equal to sigma divided by the square root of n, this is the formula we use to calculate z-values for the sampling distribution of the mean. And طبعا once we convert values, x bar values, once we convert them to z-values, we can calculate probabilities using the standard tables. Here is an example how to calculate probability for the sampling distribution. The quality assurance department for cola company maintains record regarding the amount of cola in its jumbo bottles. The actual amount of cola in each bottle varies a small amount from one bottle to another, as expected. They keep records, but their records indicate that the amounts of cola follows the normal distribution. The mean amount of cola in the bottles is 31.2 ounces. The standard of deviation is 0.4 ounce. طبعا you need those two numbers. The mean is 31.2 ounce and the standard deviation is 0.4. This is now for the sample. Sample here is the cola bottles. At 8 a.m. today, the quality technicians randomly selected 16 bottles from the filling line. Your sample has size 16. Now remember, you started with a population that follows a normal distribution. For any size sample, the sampling distribution will also be normal. The mean amount in the sample is 31.38. But the question, is this an unlikely result? Is this a reasonable result? Now remember, the population has a mean equal to 31.2. The sample of 16 bottles gave us a mean equal to 31.38. So we want to determine whether this is a reasonable, is that a likely mean for the sample, or is there something wrong with the machines? Is it likely that the process is putting too much soda in the bottle? Is the sampling error of 0.18 unusual? The first step is to convert the value we have for the mean for the sample. We convert it into a z-value. If I take 31.38, subtract the mean for the population, which is 31.20, divide by sigma, standard deviation, 0.4, divided by the square root of n, which is the square root of 16. The result is 1.80. This is the z-value. We conclude that it is unlikely the probability from the table will be that there will be less than 4% chance that this happens. But this is a very small probability, which means there is something wrong. This mean that we calculated for the sample appears to be unlikely because there's less than 4% chance. This is from the table. There's less than 4% chance. The area between 0 and 1.8 will be the area to the left of 1.8 will be 4%, but the probability that we get a sample mean equal to 31.38 is unlikely because it's less than 4%. But then there is something wrong. The process is putting too much soda in the bottles. And here is the picture. The picture always explain why this is the case. And we calculated a z-value of 1.8. For the z distribution, 0 corresponds to the average, which is 31.2. The value for the mean for the sample was 31.38, which corresponds to a z-value of 1.8. The distribution طبعا the table will show us an area 0.4641 between 0 and 1.8. That means the probability that you get this quantity is less than 4%, which is the shaded area in the graph. So that's why we decided that this is not likely, and therefore the process is putting too much soda in the bottles. We just finished chapter 8, and now we're ready to start chapter 9. The learning objectives for chapter 9: 1 is to compute and interpret a point estimate of a population mean. Number 2, compute and interpret a confidence interval for a population mean. Number 3 is compute and interpret a confidence interval for a population proportion. And the final point, 4, we want to calculate the required sample size to estimate a population proportion or population mean. There is a formula we can use to calculate the size of the sample that we need, and that would be the last thing we'll do. Let's start with a point estimate. Point estimate is a single value or a statistic used to estimate a population parameter. That's the definition. Point estimate is a statistic computed from the sample information that estimate a population parameter. طبعا احنا we've seen ان you could do that, for example, for the mean. If you take a sample and calculate the mean for the sample, this is a point estimate for the population mean. Here is another example. The Bureau of Tourism in Barbados, this is a country, wants an estimate of the mean amount spent by tourists visiting the country. What they do is they randomly select 500 tourists as they depart, as they leave the country, and ask the tourists about their spending while there and how much money they spent in the country. So your sample has 500 people. The mean amount spent by the sample of 500 tourists now will serve as an estimate of the unknown population parameter. How much all the tourists are spending. You estimated that unknown value using a sample. The mean that you calculate for the sample is a point estimate for the population mean. Now, what about a confidence interval? A confidence interval is a range of values within which the population parameter is expected to occur. This is different than a point estimate. Instead of just giving one value as an estimate, you give a range of values, and that range of value is a confidence interval. The definition of a confidence interval is a range of values constructed from the sample data, so that the population parameter is likely to occur within that range at a specified probability. The specified probability is called the level of confidence. We will see different levels of confidence. For example, a 90% confidence level for an interval, for a confidence interval, that you say, the probability that the parameter will fall within the confidence interval is 90%. And we will look at the different levels of confidence and see how to calculate confidence intervals. Now, what about the factors that determine the width of the interval for the mean R? The width of the interval, طبعا, if you're given an interval as an estimate, you don't want it to be too big. What does affect the width of the confidence interval? One is the number of observations in the sample. Then also the variability of the population, the variance of the population also affects the width of the confidence interval. This is normally estimated by the standard deviation. Also the desired level of confidence. These are the three factors that will affect the width of the confidence interval. The number of observations in the sample, which is n, also the variability or the variation in the population, which is normally measured using S, standard deviation, and the third thing is the desired level of confidence. Here is now a formula how to determine a confidence interval. طبعا the endpoints of the interval are called confidence limits. يعني we will start by يعني determining a confidence interval in the case where sigma is known, يعني if the standard deviation for the population is known. But here is a formula that gives me the confidence interval for a population mean with sigma known. But here the the interval for x bar is start with x bar minus or plus z times sigma divided by the square root of n. طبعا if the interval is centered at the mean, you add and subtract z times sigma divided by the square root of n. Now z is the z value for the level of confidence that we require. Sigma is the standard deviation for the population, which is supposed to be known, and n is the size of your sample. We will calculate it. طبعا these three things can be easily calculated, and طبعا once you know the limits of the interval, you can define the confidence interval. Here is طبعا the values for z that we need to substitute to define the confidence interval. It depends on the confidence level. For example, if we want a 95% confidence level, طبعا we need the z value from the table. The first thing, of course, is to divide 95 into half. Then the table gives us z value for just half, for positive value from 0 to the z value. If I divide the confidence level of 95%, that's 0.95 under the curve. I only want half of that, so I can use the table to look up the z value. So we are looking for an area of 0.4750 from z to the z value that we are calculating, which we will need for the confidence interval. So what we want to do now is go to the table, look up areas as close as possible to 0.4750. This is again using the table in reverse. We've done that at the end of last chapter, or 2 chapters ago. Then the closest thing, in fact in this case it is exact, an area of 0.4750 correspond to a z value. طبعا the first 2 digits you get it from the row, which is 1.9, and the column here is 0.06, so the z value that we want is 1.96. A z value of 1.96 will give you the area that you need, 95% for the confidence interval. But this is the value that you need to substitute if you are constructing a 95% interval, is a z value of 1.96. Here is an example to set up a confidence interval, and طبعا with the specified confidence level. The American Management Association is studying the income of store managers in the retail industry. A random sample of 49 managers reveal a sample mean of 45,420. The standard deviation of the population is 2050. What is the population mean? طبعا we don't know that. It's not given. The population mean is unknown, but we can use the sample mean which we know to be 45,420. We can use that as a point estimate. We can also define a confidence interval, which we will. Okay, that's number 2 now. What is a reasonable range of values for the population mean? This is now constructing a confidence interval. And how do you interpret these results? Here is the first point, and now we don't know the population mean, so we can use a point estimate from the sample, which is 45,420. Now, if you want, here they decide to construct a 95% level of confidence. We already looked up the z-value, which is 1.96. Use the formula x bar minus or plus z times sigma over the square root of n. X bar is 45,420. The z-value is 1.96. Sigma, the standard of deviation for the population, is 2050 divided by the square root of n, which is the square root of 49. This is 45,420 minus or plus 574. Subtract 574 from the mean and add 574, and that will give you the confidence limit. That will give you the interval. Then the confidence interval is from 44,846 to 45,994. Here 574 is called the margin of error. This is the number you calculated. This is what you add and subtract to the mean to get the confidence limit. This is called the margin of error. Then how do you interpret those results? Well, this is a 95% confidence interval. There is more than one way to look at the result, but they are equivalent. There is a 95% chance, or 95%, we are 95% confidence in the mean. If you select now any sample of the same size, size 49, we are 95% confident, and that will be between those two values. The other way to interpret confidence intervals is that if you look at all possible samples of size 49, that 95% of these sample means will be within those two values. Both ways are equivalent, both interpretation. Okay. The first case, the formula we used, if you know sigma, the standard of deviation for the population, the other formula we could use is when sigma is unknown. This is to determine the confidence limits when the population standard of deviation is unknown. In this case, we use the t distribution, which is a distribution. It's different than the normal distribution, but it is also bell-shaped, and it has its own tables. The t value corresponds to a z value, for example. You can use the t distribution. You can use the t tables to calculate confidence intervals. This is now for confidence interval in the case where population mean sigma is unknown. The confidence interval is x bar minus or plus t times s divided by the square root of n. Since sigma is not known, you use s now, the standard of deviation for the mean. Your limits or your confidence interval is x bar minus or plus t times s divided by the square root of n. Now this is that value for t is determined by the confidence level that you want, and we'll see how to calculate it. Let's look at an example. The dean of the business college wants to estimate the mean number of hours that full-time students work at paying jobs each week. طبعا يعني in many schools يعني even full-time students may work يعني part-time to help pay for their education. But the dean would like to know يعني the mean number of hours that those students work for each week. He randomly selects a sample of 30 students and asks them how many hours they worked last week. We can calculate the sample mean, but it is unlikely he would know the population standard of deviation, which we need for the previous formula. But basically then we will have to use this formula since the standard of deviation is unknown. But we know the sample size is 30, and طبعا the sample mean can be calculated. Okay, now it's time to look at the t-distribution. It is a continuous distribution. It is mound-shaped, and somewhat similar to the normal distribution. It is mound-shaped, and it is symmetrical. It is flatter than, flatter meaning more spread out than the standard normal distribution. In fact, both distributions are on the graph for comparison. The green one is the z distribution, which is the standard normal, and the lower one, the one in brown, is the t distribution. And again, there is a family of distribution depending on the number of degrees of freedom. We will see what we mean by the degrees of freedom, but that will determine طبعا the specific t distribution. There are many with different degrees of freedom, as we will define in the next slide. Okay, finding a value for t. First assume the population is normal. Now remember, it is sigma that we don't know. We don't know the standard of deviation, but assuming that the population is normal, using appendix B.5, this is now the appendix that gives you the tables for the t distribution. Here is how you use the table. Move across the columns identified for the confidence interval. You can look at the table. There is different levels of confidence, 80, 90, 95, 98, and 99. Select the column for the confidence level that you want, and now the levels of significance for two-tailed test is given in that column. We will explain what two-tailed test mean. But clearly طبعا you only need to use one column, and that is determined by the confidence level that you want. Notice that the column to the left gives you the degrees of freedom. The degrees of freedom will determine now the row. The column is already determined by the confidence level. The degrees of freedom will give you the row. The intersection now will give you the level of significance for two-tailed tests, and this is what we want to explain now. Here is a distribution for t. Okay, for example, a 95% confidence level, that means the area between the t values 0.95. That's what 95% level is. But now that means there's 5%, 0.05 area outside this interval, outside the confidence interval. Since this is a symmetrical distribution, half of it will be to the left of the t value, so it's 0.25 to the left of the negative value for the t, that will give you that confidence level, and the other 2.5 or 0.025 will be to the right of the positive value. But the table gives you 2.262. فطبعا here you have a 95% confidence. This is two-tailed because the area outside the confidence interval it has two tails. The area is divided equally for values above 2.262 and for values less than minus 2.62. This is called a two-tailed test, and that's the one we just calculated is for a 95% confidence with 9 degrees of freedom. Okay, to find the question is, how do you determine the degrees of freedom? Then you need to know that to use the table. The degrees of freedom actually is just n minus 1. So it's determined by the size of the sample. Once you know the sample size, subtract 1, that will give you the degrees of freedom, and then decide on the confidence level that you require, and that will give you in this example, this is a two-tailed test, and the area outside the confidence level is 0.05. If it is to be divided into two parts, two-tailed, then the t-value that we want is 2.262. And that means our confidence interval is between the negative of this value and the positive for symmetry. And the area outside is divided into two equal halves. Each is 0.025. So we'll do more problems that will explains how to use the t-distribution. Here is an example. A tire manufacturer wishes to investigate the tread life of its tires. The tread life is normally measured by thickness. In a sample of 10 tires driven for 50,000 miles revealed a sample mean of 0.32 inch of tread. قلنا the tread how much the tire is used is measured in thickness. In this case, the sample size is 10 tires. The mean turned out to be 0.32, and the standard deviation, now this is for the sample, 0.09. The standard deviation for the population is unknown. We want a 95% confidence interval for the population mean. Would it be reasonable for the manufacturer to conclude that after 50,000 miles, the population mean amount of tread remaining is 0.30? And that's what we found from the sample. The sample mean gave us a 0.32 inch of tread. But the question is now, using the confidence interval, is 0.30 a reasonable amount to expect? The first step, of course, is to construct the confidence interval. This is using the t-distribution, and the standard deviation of the population is unknown. It is x bar minus or plus t times s divided by the square root of n. Here, use s, the standard deviation for the sample. It is 0.32 minus or plus 2.262. That's the t-value that we got for a two-tailed test at 95% confidence level. This is multiplied by 0.09, which is the standard of deviation for the sample, divided by the square root of n, which is the square root of 10. By the way, here we used, in the table, we used 9 degrees of freedom, and the sample size is equal to 10. Then this is 0.32 minus or plus 0.064. Then the confidence interval, the limits for it, the endpoint is from 0.256 to 0.384, with a margin of error اللي هو طبعا 0.064. The manufacturers can be reasonably sure, 95% confident, that the mean remaining tread depth is between those two numbers. And that's why we constructed the interval, and it is a 95% confidence interval. Then we can be 95% confident, and the mean will fall within these two numbers, between 0.256 and 0.384. Is then this case is 0.30 reasonable? Well, it is in this interval. فإذا it is possible, it is a reasonable number. because since it falls within the interval and there is 95% chance in that it would fall within these limits, then it is considered to be a reasonable value. There is one more thing that we have to say about this is a 95% interval. If you continue to take samples of the same size, the expectation in the 95% of cases, the mean will be within those two values. That means it's not always, the value will not always be in that interval. And 5% of the time, the mean will be outside that interval. But at least 95% of the time, it will be within these two limits. Next, we would like to construct more confidence interval. This time, we want to do it for a proportion. Here you have, well, first of all, let's define what a proportion means. This is a fraction or ratio or percent indicating the part of the sample or the population having a particular trait of interest. You may be interested in knowing the proportion of smokers مثلا in a society or any other ratio. It will be a fraction and it will be a number less than 1. طبعا that can be calculated for a sample, and in some cases you can do it for a population. A sample proportion, which we will use P for that, is found by طبعا take the number of successes divided by n, by the sample size. If you remember the problem we did about union members, we had a sample of 5 workers, and we were wondering the probability that 4 of them were union members. But here, success was a number of union members. Anyway, the proportion can always be calculated for a sample. Just take the number of successes divided by the sample size. But that's the starting point. For a sample proportion, it's simply x over n, the number of successes divided by n. Here are examples, and طبعا the next thing we want to do is to see confidence intervals for proportions. The examples, مثلا Southern Tech Career Services, that's a company that advises people on their career. Anyway, they report 80% of its graduates enter the job market in a position related to their field of study. طبعا there's certainly cases where people graduate from they study a field of study but they don't end up working. But this company claims 80% of the graduates will work or will enter the job market in a position related to their field of study. So this is a proportion now, 80%, 8 out of 10 of their graduates will work in the same field that they studied. Here is another example of a proportion. A recent study of married men between the ages of 35 and 50 found that 63% felt that both partners should earn a living. This is again 63% is a proportion for a certain group who believe that both husband and wife should work, should earn a living. We will see طبعا more examples of a proportion and also see how to calculate confidence intervals for a proportion. A population proportion is identified by pi. There is 2 requirements. The binomial conditions have been met, and that's why I guess we use pi, which was the probability of success, if you recall. But the binomial conditions must be satisfied. The values for n pi and n1 minus pi should be both greater than or equal to 5. If you recall, for the binomial distribution, n pi gave us the mean, and n we were able to use the parameters to calculate both the mean and standard deviation. For us to do a confidence interval, the two requirements is that we have a binomial distribution, and the other condition in the n times pi and n times 1 minus pi should be both greater than 5. We construct the confidence interval for a population proportion with the following formula. This is now for a proportion, confidence interval for a population proportion. This is starting with the proportion for the mean, for the sample, p minus or plus z times the square root of p times 1 minus p divided by n. And here again, z is the confidence level the confidence level that we require. This is the z value for that. And p طبعا is a proportion. This is now for a population. Confidence interval for a population proportion. You can use this formula to construct the confidence interval. Here is an example. The Union representing the Bottle Blowers of America, or BBA, is considering a proposal to merge with the Teamster Union, with another organization. For at least 3/4, 75% of the members of the BBA members must approve any merger. فطبعا they cannot, it's difficult to check with all the members. They take a random sample of 2,000 current members, reveal that 1,600 plan to vote for the merger proposal. فطبعا the proportion can be calculated easily. 1,600 divided by 2,000. What is the estimate of the population proportion? طبعا we want an estimate for the population proportion to see what chances does the proposal have to pass. The question now also, can you conclude that the necessary proportion for that organization members, would you say you have enough to approve the merger or not? And you have to explain why. This is all will be based on the confidence interval. The first step is to calculate the proportion. We know that 1,600 in the sample plan to approve the merger, and you vote for the merger, where the proportion is 1,600 divided by the size of the sample, which is 2,000. This is 0.80. Next, I want to construct a confidence interval for the population, based on the proportion we have from the sample. We choose a 95% confidence interval. Then the confidence interval is p minus or plus z times the square root of p times 1 minus p over n. Plug in those numbers. The z value for 95% confidence is 1.96. If you do the necessary calculations, you will get 0.80 minus or plus 0.018. Within the endpoints of the confidence interval, subtracting and adding 0.018, you will get 0.782 and 818. Okay, the merger is likely to pass, and you need 75%. You need 3/4 of the members to vote for the merger, and the confidence interval will tell you that there is 95% confidence in the value, the ratio, or the proportion of the people who will vote is between 78% and 81%. But there is a very good chance you will have enough votes to approve the merger. Then you only need 75%. Next thing, or this is probably the last thing we'll do in this course, is determining the sample size for the mean. If you recall, the sample size is important, especially if you don't know that the original population is normal. We have a formula that help in determining the sample size for means. When you are trying to estimate means, this will tell you what is the sample size, what is the best sample size for the mean. So there are three factors that determine the sample size when we wish to estimate the mean. First of all, the margin of error, how wide should the interval be. طبعا احنا الحين we're estimating the sample size, so one of the things that affect that is the margin of error, how wide the confidence interval is. The desired level of confidence, one example we worked with was 95. You could do 90%, you could do 98. The level of confidence will also affect the sample size. And the last thing, of course, is the variance, the variation of the population, as measured in sigma, مثلا the standard deviation. The formula to determine the sample size for the mean, and طبعا you have to round this number. This is the sample size for estimating the population mean. N is equal to Z times S over E, everything squared. طبعا Z, as usual, will be the Z value for the confidence level that we need. S is the standard deviation, and E is the margin of error. طبعا that number will not be a whole number. The practice is to round up any fractional result to the next whole number. Round it up. We will do an example or examples to see how to estimate the size that you need for a sample for a population mean. Here is an example, and then a student in public administration wants to estimate the mean monthly earnings of city council members in large cities. طبعا I assume this is in the United States, so there's many large cities, and this researcher wants to know the mean monthly earnings of city council members in large cities. She can tolerate a margin of error of $100, plus or minus $100. This is your margin of error. She would also prefer to report the interval estimate with a 95% level of confidence. That طبعا will determine Z. The student found a report by the Department of Labor that reported the standard of deviation of 1,000. So what is the required sample size? Using the formula, N is equal to N times sigma over E, everything squared. Z طبعا for a 95% confidence level is 1.96 times sigma, which we know to be 1,000, divided by the error, which is 100. This is 19.6 squared, or 384.16. And طبعا we want to round this up. A sample size of 385 would be the required size that we need. The next thing is we want to see how to estimate sample size, this time for a proportion. But again, there are the same factors that determine the sample size for estimating a proportion. طبعا the margin of error, E, the desired level of confidence, and a value for pi to calculate the variation in the population. We need a value for pi. Remember the probability of success, which is a proportion, of course. The formula to determine the sample size for a proportion is N equal P times 1 minus P times Z over E squared. طبعا P here is a proportion, and E is the error, and Z depends on the confidence level. Here is an example. It's probably the same student, but this time we want to estimate a proportion. The student in the previous example wants to estimate the proportion of cities that have private refuse collectors, اللي هو garbage collectors. طبعا some cities have private, يعني they work for the city, and many cities hire companies, يعني they're not private. She wants to know the proportion of cities that have private refuse collectors. The student wants to estimate the population proportion with a margin of error of 0.10. She prefers level of confidence of 90% and has no estimate for the population proportion. What is the required sample size? طبعا because we don't have an estimate for the population proportion, we're using 0.50 here. The sample size is 0.50 times 1 minus 0.50 times the z value for now 90% is 1.645 divided by the margin of error, which is 0.10, everything squared. If you do the calculation, you should get 67.65. طبعا we round up, but the student needs a random sample of 68 cities.